Is that an open circle at 14 or closed?
Closed.
Closed.
Thanks.
No problem.
Thanks, Art, because it
No
kind of looked like that. And when it's right here, kind of sloppy. That's a semicircle. So make a note that this is made up of straight line segments and a semicircle. That would have to be told to you, because when you look at that, you know, even if it's made with software, you'd have to be told like this right here is a semicircle. This got down to -4. That's a semicircle. What's the area of the circle again?
5 squared.
Pi squared. Okay, good. This is velocity. This is about velocity of a bug. Right here, this represents the velocity of a bug. It's just traveling up and down a vertical wire. Right? Now, when you see this, when it's above this x-axis here, right? This is t. The bug's traveling upward. And when it's below, it's traveling what? Downward. Cool? Everyone got that? So this bug could go up, go down, going up, and here's the first thing. We gotta find.
Displacement and distance.
Yeah, and I think I'll ask that, like, in a later question, I'm gonna put that down, about the distance and velocity or displacement, words like that. Well, the first thing we're gonna find out is the integral from 0 to 14 of v of t dt. The equations aren't given, but we can see that's a straight line, and when that's a semicircle, and that's a straight line. Well, doesn't this deal with area? So we'll start out and we could say, all right, to get this integral, find that area of that triangle. True? Find the area of that triangle. Then we gotta get the area of this semicircle. And we add stuff together, but of the three areas, which are we gonna assign a negative value to?
The circle.
Yep, the semicircle, because it went below the x-axis. That's what happens with integrals, right? That's what happens with integrals, we know that. So here we go. Let's start with getting this area of this part. All right, what's area of a triangle?
Half base into
Half
height.
base height, right? Okay, so half 4 times 8.
32.
Half 32? 16? All right, so in here we're getting area 16. All right, that tiny triangle at the end. And I did my best there, Cal. It looks like a height of 2, right?
2, yep.
It's a height of 2. All right, at 2. The width is 2. Half of 2 times 2? 2. We got a 16 plus a 2.
This is half.
Area of a circle is pi r squared. This is half a
So
circle.
half pi r squared.
Love it. Half
Pi r squared.
pi radius squared. The radius is
4.
4. Half pi 4 squared. What's that? 8 pi. So when I write this answer, I could say it's 16 plus 2, which is what? 18, subtract d8 pi. Now you can leave your answer like that. Because we know pi is irrational. Unless you want to use 3.1415926 and multiply it in there, but leave it like that. Alright. Here, make this letter A. Or your letter. Letter B. Evaluate this. I should have put evaluate, right? Evaluate. Definite integral. Evaluate. 0 to 14. Boom. The absolute value of d of t. Boom. dt.
This is the displacement, right?
Oh, good. I'm going to ask those questions in C and D. And when we get to C and D, I'm going to ask you the displacement of this bug. And then match out the total distance of this bug. All we have to do is look back on A and B.
So
But, oh, go ahead.
wouldn't it be 18 plus 8 pi?
You got it. Tell us about that. You nailed it. What's going on with absolute value functions? What happens to any graph when you put the absolute value of it? It makes any portion underneath it do what?
Positive.
Flip upside down. Let me say it again. What's the absolute value of any function? The graph would just take anything below that x-axis and just what? Flip it up. So if you're thinking about that graph right there, you're like, just a miniature graph, you're like, that graph did what? It went like this, yeah. But this thing went like that, right? And then it had that little piece at the end. So in this case, all right, you nailed it. What are we going to do with all these numbers? It'll be 18 plus 8 pi, right? That would be this answer. Leave it like that. No units, we'll just leave it like that. All right, so now, which one of the following, for the earlier ones, finds the displacement of the bug?
The first one.
And then, remember it was a bug, the bug was crawling up and down a vertical wire. That described the velocity of the bug, right? At some point, the bug had a velocity of 0. At some, from time equal to 4 to time equal to 12, the bug had negative velocity, right? Now, if you think about this, what was going on with this bug traveling up and down this vertical wire, it only traveled for 14 seconds. From 0 to 4, the bug was traveling up the wire. And at time equal to 4, the bug stopped, turned around, and the bug went what? Traveled down the wire. And then at 12 seconds, the bug traveled up the wire. Cool? So it did like this. It was like, it went up for 4 seconds, then it went down, then went back up. Which one of these finds the displacement of the bug? That's how far from the original position that bug is. And which one of those other ones, A or B, finds the total distance? The total distance traveled by the bug. Total distance traveled by the bug. And you nailed it. Which one was it, Art, for displacement?
A.
A. Integrals of the finds displacement. What do you mean by displacement? How far from the original position the bug was. So if you're talking about me, like traveling right to left, if I went like this, and then I went back to here, to the same spot, my displacement is 0. Right? We're trying to find the displacement of the bug. That would be A. So which one's the total distance? So this finds total distance. If we're talking about that this v of t is representing the velocity of the bug, but it could be the velocity of a particle. Right? Total distance would be the integral, the absolute value of that, because what we do is we add up all those parts. We just reflect everything like that. Everyone okay with that? All right. When you do ask these questions, yes, you got to make sure that you give straight lines to the students. If you do any type of curve, then you got to make sure it's like a semicircle or a quarter of a circle or something like that. Something you're familiar with in terms of getting the area, like a triangle, or a square, or a rectangle, or a circle. Cool? Awesome. Hey, eventually we'll spend the bulk of the day in 5.5 on the substitution rule with U subs. You'll like that, but I'm in 5.4, and there's a specific problem I wanted to do, because it's can kind of throw people off, and it's number 29. This is a 5.4. I didn't want this one to stump you. Four plus 6u. All right, I'm gonna use x. They used u, I'll use x. Dx. Actually, it was a definite integral, but I'm gonna make this an indefinite integral. So I actually changed it a little bit. Maybe when we're done, we'll go back and make it a definite integral. But here, would you evaluate the indefinite integral? Okay, doesn't that mean we're going to find the antiderivative?
Mm-hmm.
But it looks bizarre. we see this expression like this, we might think, oh, was it a quotient rule or something like that? Well, that was derivatives. And we gotta use your suggestion from math class, Bill Rash. Do you remember what it was? How do you deal with something like
X
that?
to the power half,
Yeah, just split it.
Yes!
split it.
You like split it, split that fraction, right? That's the idea. You like, think of this as 4 over the square root of x separately, plus 6x over the square root of x. Some of you are so awesome, like, you do that in your head, you know how to, simplify that and get everything up in the numerator. Well, I'll take it slow. That's an x to a 1/2 in the denominator, right?
Mhm.
Alright, so I'm just gonna take it slow. That's a 6x to a first over a 6 over an x to the 1/2 in the denominator. So first I do.
Mhm.
Now, in this scenario, don't we just subtract powers?
Exactly.
Alright, what's 1 minus a half?
Half.
A half, good, so this one's just gonna be 6x to the 1/2.
Maybe negative.
Nope, because it was a 1 minus a half. It'd stay positive in the numerator. Hey, Amber, just for a quick example, look at that guy. And you go, oh, I could simplify that to just be, see, it stays positive, doesn't it? Good deal. But Amber, this one is.
That's going to be 4x
So I gotta get that up there, alright, what is it?
minus half.
There you go. So Amber, maybe you were thinking of that one. That's gonna be
Yeah.
negative. That's the one that's gonna have to be at a negative exponent. dx.
You have to keep adding that dx.
Yep. And I know you go, gosh, and I might even forget to write it one time. You can correct me. It goes away when we find the antiderivative. It means with respect to x. I think it's important. You'll get in the calc too. You'll have that. Ooh, and then you'll have like this. So it's important you know which variable you're integrating with respect to in regards to this. And then you'll get something like this. Ooh, you get a triple integral. And you want to stay organized, so plus today it becomes important. You'll notice this is important today. But yeah, from time to time you might just go, hey professor, you forgot the dx. Alright, let's do that. Pump it up by 1. What's a negative half plus a 1?
Half.
Alright, look. 4x to a negative 1/2 plus 6x to the 1/2. Antiderivative, you said 4x to the half, then you divide by a half. That looks ugly. What does it mean when you divide a half now?
Multiply by 2.
Good job. A lot of you do it automatically. You're like, if you're going to divide a half in math, you're like, that means, here, multiply a 2. True?
Mhm.
Multiply the reciprocal? Alright, 2 times 4 is just what?
8.
Alright, we got,
Wait, what?
Part of the
Multiply
answer?
by 2? Oh, you're multiplying by the reciprocal.
you nailed it. Plus, alright, you gotta pump this
3 half.
x to the 3 halves.
Divided by 3 halves.
Amber, would you flip that for me? Because
Two
it looks
thirds.
stupid.
Yeah, so it'll be
2/3.
2/3.
2/3? Alright, so I got enough room in here, I think. Look, plus, and I'm just gonna take this off and multiply 2/3 to the 6, right?
Mhm.
Let me get that out, because it looks weird, right? What do you mean 6 divide 3 halves? It means multiply 2/3 to that 6.
That
Well, that was 8. What's 2 times 6 divide 3?
4.
4. And now, Josephine, it's an indefinite integral. That means we didn't have these lower and upper limits here. You go, what do? You just put a plus.
C.
C. Plus constant. Plus Charlie. And if you want to be cool, you can make that a square root of x. But you can leave it like this. That's fine.
Why did you divide it by 1/2?
So whenever we do, we'll look at a simple example. You and I integrate x squared. We go, oh, the definition is x cubed over 3. See what we're always doing? We're always saying pump this up by 1, then divide by that value.
Oh, so that's that.
That's the antiderivative rule for these, right? These little monomials. The next these expressions. And you go, oh, well, it's x to the 1/2, you gotta divide by a half. Or this one became x to the 3 halves, you gotta divide by 3 halves. But it's weird when you divide a 3 halves. We say, oh, just multiply a 2/3. You do it a lot too, because sometimes you get 5 halves and 1 halves and 3 halves. Yep. Does that make sense? Alright, now, change the problem just a tad. What did this problem have? Evaluate the definite interval. Now what were the numbers? 1 and 4. So if it's a definite interval, 1 and 4, 1 and 4. 1 and 4, 1 and 4, a 1 and a 4. And then once I do the antiderivative, Amber, I don't put that dx anymore, do I?
No.
I don't. I don't have to put the plus what?
Let's see.
Plus c,
'Cause you
but I put this vertical line here, and I'm going to substitute what numbers? 4 and the number 1, and I'm substituting it for what letter? X. You start with the 4, right? So you get 8 times x to the 1/2, that means 8 times 4 to the 1/2, plus 4 times 4 to the 3/2. I'll put a big parentheses around it. And then what do I have to substitute up?
Negative.
Put a 1 in there, right?
1.
1 to the 1/2. Plus 4 times 3/2. And what is between these every time?
Negative.
Subtraction sign of negative. It's always a subtraction, right? Put this in, subtraction, put this in. Now, how do you do these? You don't need a calculator. Your calculator can do it. Like 4 to the 3/2. It means the square root of 4 and then cube it. This means the square root of 4 raised to the first power. All right, let's start with this one. What's the square root of 4?
2.
2? 2 to the first power? 2? What's 2 times 8?
16.
16. Trust me, Owen, you can do this. Just don't, we're doing PEMDAS. You gotta do exponents before you do multiplication, right? Please excuse my dear Aunt Sally, order of operations. So let's do this first. Square root of 4 is 2.
2.
2 cubed is
8.
8. And then 8 times 4.
32.
Does anyone see that? Is everyone okay with that? It's the idea of something you can actually do mentally. Everyone in here, we all know the square root of 4 is 2, and then we all know 2 cubed is 8. All right, I got all that. Now I got to subtract. Oh, you got to love ones. Everyone, 1 to the 1/2 is a 1. 1 to the 3/2 is a 1. So it looks like our answer is 16 plus 32 minus this 12 over here.
36.
Yep. You got it. 48 minus 12, 36. Definite integral. We got a definite value, right? We evaluate it, we get a value. What does it represent? Well, if that was velocity, that represents displacement, right? Right? You go, oh, it represents area under curve, but I gotta be careful with that wording because sometimes the function may go underneath the what?
Like
X-axis, and that gets subtracted out, so you can say the word net, N-E-T, for like net area. Right? And that's why this section, they talk about the net change theorem. This idea of net change, right? Net change, but that's what that is. Isn't that good? That was the only one I thought it was weird. Did anybody see any other goofy ones in here? Or from the ones I assigned? If we do, would you holler at me tomorrow? Would you bring up that problem tomorrow? There'll be time to do that. There'll be time tomorrow, even on Thursday, to do some of these problems in the textbook that you're like, I tried number 11, I couldn't get that one.
So the test is not on Thursday.
Right, we're gonna have it Monday. We're gonna have it Monday. We thought it was a good idea. Everyone can take the weekend and just
It's a
go to
good
review.
idea.
Some students will probably start, they might start even prepping for the, getting prepared for the final next week, but they'll still know that they're getting ready for that test on Monday. They had that weekend to do it.
So the final is on next Thursday?
That's right. You could actually take it Wednesday if you would prefer to do that. The reason I like to do a Wednesday, Thursday option, there are many students in this class actually, this isn't their only class. They have another final on that Thursday. And isn't it tough, 2 finals the same what? Not only the same day, but back to back almost. That's wipe people out. So it's like, some of them like to have that. Can I do this Wednesday? I'm gonna prep for yours, and I'm gonna start prepping for the next one, or vice versa. Cool?
Do your class on Tuesday?
Yes.
Yes.
Class would be Tuesday. That's a good day, because that's review. That'd be review day, review anything, We'll just be reviewing. I'm hoping that on Thursday I'll be reviewing for test 4, but I have a feeling a lot of students are gonna start asking me questions. Once they're like, I'm confident with the material in chapter 5, they might start asking me questions about like earlier tests and start reviewing early, and that's okay too. We can work that in. Cool? Alright, let's have some fun. This is awesome. Everyone, you remember chain rule?
Mm-hmm.
This is the only rule we learn in this Calc 1 course. You go, what about product, what's the opposite of product rule? We don't learn it here. I wish we could, it's fun. Right? It's called integration by parts. Well, we don't do integration by parts in Calc 1. We used to, they took it out. They put it in Calc 2. All right, kind of miss it, it's fun. If anybody in here wants to know integration by parts, let me know, I'll show you, but we do the substitution rule. But it's basically the reversal of chain rule. So it is by far the most important rule. Just like chain rule is like the killer rule, substitution rule. Like killer rule. So, let's look at one. We haven't needed the substitution rule yet. That's because everything we've done is so far been stuff like this. Or what? You don't have to copy these, stuff like this. These types of examples. We haven't had this, let me say that word, composite functions. We haven't seen any of those composite functions yet. So, here's my first one. Da-da-da. Evaluate. Hey, is this a definite interval or an indefinite interval?
Indefinite.
Evaluate the indefinite integral. Well, ladies and gentlemen, we need the substitution rule. See, the integral of e to the x is e to the x, right?
Mm-hmm.
Who recalls the derivative of e to the 2x?
2.
2e
To
to
the
the 2x.
Gosh, you're good. Seriously, that was good. That was loud. 2e to the 2x. Chain rule, right? Well, this is going to be like that backwards. So the answer should kind of be backwards. Would you expect that? Okay. Would you expect the answer to this be kind of backwards of that? You said the derivative is what? 2e to the 2. Let's see what comes about. What do? We do what's called the substitution rule. And appropriate letter, we got to use a letter other than x because we're going to do a substitution. So in calculus, we like to use the letter u. And that's why we call these u cells. All right, so we're going to let u equal something. We do it off to the side. So let u equal something next expression. Well, I'll give it away. This is the first one we're doing. We're going to let u equal to 2x. So what is u? If you wonder what is u every time, it's usually something under a radical, or u is something up in the exponent, like here. Maybe something in a parentheses in a problem. But through experience and through practice and through the problems we work in class, you'll get used to it. You'll know how to find or use, or identify what you should let u equal to.
Is it like the same thing as a G?
Yes, it is. Because it's just like a G. And we're going to be doing it backwards. It's just like a G. We could have called these G subs. That's exactly right. That's exactly what it is. It's just like that. So I'm going to let the u equal to what?
2x.
The 2x. Because it is. It's like composite function. E to the 2x, like e to the u.
Oh.
Now, that's step one. But it's always a three-step process off to the side. So, for the next hour, get used to this. Step 1, step 2, step 3. Sometimes you can complete it in 2 steps. We'll talk about that. Step 2. Now that you let u equal to something, differentiate both sides with respect to x.
So du over dx equals to 2.
Du over dx equals, what's the derivative of
2.
2x, excuse me. 2?
2.
And du dx, now I'm going to erase this. Does everyone have a pencil? I want to show you how we're going to write step 2 every time. It's appropriate to write this actually as the differential du. So I can put this dx next to the what? 2. So do you agree du dx, the derivative of u with respect to x is a 2? But every time in step 2, we're going to put this dx here. We're multiplying a dx on both sides. We're going to consider this du equals 2 what?
dx.
Yeah, we'll do that every time on step 2, every time. So you'll get used to it. You go, all right, du dx is 2, but it means du equals what? 2 dx. Leave that dx over here on the right side. Now step 3, I'll be clear on this step. What are you doing this? Notice this is off to the side, by the way. You notice this? I'm not working the integral yet. We're going to come back to this. It's like I'm off to the side here. In step 3, if any constant emerges on this right side, I want you to divide it. I want you to divide it on both sides of the equal sign. So 2 emerged, right?
So half
Let
of
me say it again. You'll get used to this, but if a constant just emerges, any kind of like a 2, a 5, a 3, it emerges there, we're gonna do what? We'll divide it. Now what if a variable emerges? No, I don't want you dividing it. Okay? Now you'll get good at this, and you'll be able to play with this even more often. You want something that works every time, you're like, okay, any constant pops up, I will divide it on this side. Oh, go ahead.
And you don't have to do that if that's not okay.
Oh, so if there was no constant there, just like an invisible 1, or 1 was a constant, then we'd be good to go, and we'd go substitute. Good deal. Hey, and make a note, Josephine, what if variables popped up over here, like x's and x squareds and x cubes, things like that? Variables, leave them here. I only want you to divide into what? A
Constant.
constant. So what would this be? What would dx equal?
Half of du.
Half a du. Some of you may say du over 2, but I like that. I like the way you said it. I like the half of du. So 1/2 du. So here's the 3 steps. We'll do it over and over and over again. Now what do? We substitute. So it's a substitution. What do we do? All right. We'll start with this guy. So I'm going to box him. That is going to go replace the what?
2x.
2x. Let me say this again. This u is going to come in here, right there, and replace, substitute for the 2x. So maybe I'll take an arrow and go, here, you're coming in. Right there, and what are you doing? You're going, what am I replacing it with? U. Cool. And then, this guy, in step 3. What's that replacing?
dx.
That's going to replace the dx. And what you notice is we're changing this whole problem and putting it in terms of u. Okay? So this will replace the what? Yeah. So now remember the dx is important. Right? Before we were just like, gosh, we just wrote it every time. This is with respect to x and these integrals. This is now going to replace this. Now everything's going to be with respect to u. The only thing I got to make sure when I do this, you're going, I'm putting what here? 1/2 du. Now I'm going to write it, then maybe I'll change this. Look, 1/2 du. Does anybody have a suggestion where I should put this half?
All the way to the left.
I think it's a great idea. When you get these fractions like this, like a half or 3, you might find it easy just to put it way over here in front of the integral. Because doesn't it look weird over there?
Mm-hmm.
It does. Like this e to u, half to u. I recommend taking this half that's sitting right here. I know it's right next to it, but I can put it over here. And then now have just what right here?
1/2 plus e to the u.
Let me write it again. You said what? 1/2.
S e to the u.
Now I want you to glance over this to make sure we didn't make any mistakes.
Do you have?
I shouldn't have any x's left in that expression. Do I have any x's?
No.
That's the idea. I've now substituted. Everything's in terms of u.
Now why'd you put the du?
Oh, that's important because every time you do an integral, it's got to have like du or dx or dt, right?
Yeah.
All these are Amber. We'll over and over. We'll use u. So we always have this du there. Sterling.
What's the S called?
The s, it's an elongated s, right? And it's just the integral. This means that we're finding the antiderivative. But it's this is elongated s because it did find like the Riemann sum of all the rectangles that we were doing earlier. All right, everyone, what's the integral v to u?
E to the power u.
E to the u.
E to u. Oh, the integral v to x is e to x. What's integral v to u? We have manipulated this problem so we can integrate it. That's what we're doing. That's the game here. So look. Integral v to u is e to u. What about the constant? Constant rule. Leave the constant in front. But this was an indefinite integral. I have to put a plus what?
C.
Plus c. It was indefinite. Now,
No.
this was step 1. If this was step 2, if this was step 3, and if step 4 was substitute, step 5, resubstitute.
Can I ask you a question?
Yeah.
Now this half, shouldn't it be also go to C also because do you have to put a bracket around it?
You could if you want.
Okay.
Hey,
Why'd you take
that's a
that
good question. He goes, should I put the half to C too? You could if you want, but this is an unknown constant. So half times C is the same as some unknown constant. What's
Got
C?
it.
So I couldn't take off. Art wrote half C here. I mean, yeah, it's some unknown constant. Half times C.
Why'd
You
you
could
take-
do that if you want, but you can just put plus C.
Got you.
Why'd you take out the s?
Oh, because we found the antiderivative.
That's it.
Yep, because we integrated it. The integral v dx e dx. So the integral of e to u is e to u.
The S was to, oh, it's
Integrate,
like,
yeah.
You got it. Now, I want step 5. So I'll review this, right? Step 1, boom. Step 2, boom. Step 3, boom. Step 4 was substitute. Step 5, resubstitute. We can't forget this. It's important. This problem originally had what letters?
X.
I cannot leave my answer like this. It originally had X's, the final answer has to have what? So I have to resubstitute. You gotta go back earlier in your work. What did you let u equal to and resubstitute it? What was u?
2x.
So the final answer is 1/2 e to the 2x plus 1. There it is. Now how could you check this? You should be able to check every one of these.
Is half of,
Take the derivative of this. You should come right back to this. E to the 2x. Isn't that cool? You can check every one of these. So when you see something going on here, we said the derivative with respect to x of e to the 2x by chain rule was 2e to the 2x. Well, what was the integral of 2x dx? What did it come out to be?
half of the,
See how it's almost like opposite? And a lot of you will see patterns like this, and you'll be like, I don't even have to show work. I know what this is. And that's actually a good sign. Can I give you an example? What if I gave you the integral of e dx, e to the 3x dx on the test?
so 1/3 it,
130.
I heard it. See how loud that was? You're like, it's just going to be 1/3 e to the 3x. You got it. Oh, question.
That's all, that's
Oh, good. Hey, so yeah, you go, then I have to show you that work. Because I'm so confident I know that's what it is. So if I gave you, ready? Integral of e to the 5x.
1/5.
That's what you would get. I think it's great. I think it's super when you're like, I know what'll happen in here. But there's going to be some problems you're going to definitely have to do this off to the side. You'll be in calculus 3. You'll find yourself still doing this at times. Eventually, some of you will get so good at these, you'll do a lot of these in your head. You'll do this mentally. There's some calc instructors out there, teach calc 2, and they kind of get upset when they have to show this. They expect you to do it mentally. Don't worry if you have to write this stuff all the time. I think it's good to do that. Cool?
What happens if it is e to the power 2x squared?
Oh, say it again. I love this.
E to the power 2x squared.
Yeah. Or how about just e dx squared?
Okay, yeah, that's good.
I love that. And how about just this? I'm not giving you that one on a test. Wouldn't work. It wouldn't work. Now, is there a way to look at this? Mathematicians looked at this one carefully because they knew the u sub process, the substitution rule wouldn't work there. I want to show you what would work. So here's going to be my second example. I'm going to put e dx squared, but in front of this, I'm going to put an x. Okay? Now this would work. Now let me get all this out of the way. Now we're going to let u equal something, right?
Mm-hmm.
Can I take out the word let?
Yeah.
We always let u equal to. This one will work, and Art, I think it's going to help you discover why e to the x squared alone would not work.
Okay.
So I think this is a really good question.
Is this going to also employ prodigal?
Good question. Because it has a product, it's got the product, but now it's got that e to the x squared. It's like a, it looks like
I
product,
see why.
but it's got that composite function of e to the, composed of, exponent e to the x squared. So this really is going to, it's totally going to fly with the u subs. I want to see what's going on here, though. And what's that power? X to the what?
Squared.
Squared? What's this power? X to the?
1.
You'll notice in a lot of these problems, I can't say it's every problem because some of these have trig functions and logarithmic functions, but a lot of times you're going to see a power difference by 1.
1.
Let me say that again. On a lot of these, you're going to see a power difference in the exponents by what? 1.
Mm-hmm.
Do you follow what I'm saying there, Amber? Like power, like 2, x to the 2, but this is x to the what?
1.
First, you might see like x to the 5th, and I guarantee you this one over here would be x to the 4th. And you go, why is that so? Why are they giving you these in this section? Because step 1, we got to let u equal something. Where when I want you to let u equal to the one with the higher exponent.
So,
I see an x and I see an x squared. So let u equal to what? X squared. Why is this so?
now I
Because
get
tell me about step 2.
D,
What do we do in step 2?
differentiate it. So,
We
okay.
always differentiate with respect to x, right?
Uh-huh.
And when you take a derivative,
It's
du equals, what happens to this power?
2x
It
dx.
decreases by 1. Yeah, 2x And I'll put the dx here, right? I'm gonna do that every time.
Then divide
But
by
this is
2.
why, and I wanna point out, you're gonna see this, you're gonna go, oh my gosh, every problem practically. I can't say it's everyone because you get trig functions and logarithmic functions, etc. But a lot of times the power difference is a power difference by what? One integer. Like x to the 8th, x to the 7th. X to the 6th, x to the 5th. Because of that right there. So now, Josephine, do you remember step 3? I said divide out the what? The constant. Now when a 2 came up, so I'm going to divide what? 1/2 du. And why am I doing this? Now notice, this is sometimes a mistake. Students first learn substitution rule, like maybe online or something. They think they divide the x too. No, leave everything in terms of x over here. Because we're trying to get rid of x. We're trying to change all the x's to what? U's. Does that make sense? Does that make sense? Look, see all the x's in there? Don't Raj, we're going to get rid of all those x's. They're all going to turn to what letters? U, right? So when I'm this third step, I just divide the 1/2. U. All right, put a box around this. All right, what's that replacing? All right, here, get it out. That becomes what letter?
E,
U.
U.
After a while, I won't have to do that every time, but first 3 problems, I should do this. Shh, you're out. This is it. All right, and this third guy.
No, x dx.
Yes, this is going to substitute for the dx, but also the what?
X.
Does everyone see that? This will so that's what I mean. We're getting rid of all x's. This is going to substitute for the x and the dx. So here, you're out, and you're out, and what replaces it? I'll put it down here, but everyone remember our suggestion? Where should I put the half? Put it in front. Makes it look better. Like it makes it smooth, right? So let me write this again. Put the half in front. 1/2 here. E to the u, no more x's. Now I'm going to go to u, Amber. We're going to integrate this. Well, what's the integral v dx? E to the yeah. What's the integral v to u? E to u. So I'm now able to remove this, right? I'm performing the antiderivative of e to the u, and I get e to the u. Plus a c, right?
Yeah.
Now what about that constant? The constant just what? Hangs in front. You don't have to distribute the half to the c because it's some unknown constant, right? Cool. Now, don't forget the last step. You get the test back, you go -1, oh, I forgot to what? Resubstitute, right? Resubstitute, I can resubstitute. What was u? Just gotta go back and look. U was an x squared, so you get 1/2 e to the x squared plus c. Now, do you all remember Art's question? He says, what about integral v to the x squared? Can you see why it wouldn't work?
Yeah, because there is no x over there.
There's an x squared and there's no x to the first here.
Yeah.
You see? We couldn't do e to the x cubed, e to the x to the 4th. But if you're curious, like mathematicians, like those other rules don't even work with e to the x squared. Now you could back up, it was a definite integral, we could estimate it with Riemann sums. That'd be cool.
No, what if they're the same power, like x to the e to the power x? You can do it, right? So x equals to, let's see, if it's x e to the power x, you can do that, right?
Oh, what was it again? X e to the
X.
x e to the x you could do.
Yeah, we can do that.
But I want to point out everyone, Calc 2.
Oh, doesn't count too.
I wish I was able to teach this. If anybody's curious about this rule, it's called the integration by parts. I call it IBP. And that's product rule right there, Cal. This is the reversal of product rule. It's called integration by parts. We used to have it in our Calc 1 courses. Some courses across the country still keep it in Calc 1. Okay? It used to be like, everybody know the AP exams? You know, Calculus AB? They used to have it in the AB. They took it out of AB. Sometimes they put it back. It's one of those. It's right on the cusp of Calc 1, Calc 2. They cut it off at one point. So, but it's fun, but that's what you'd use. And it's quick. And you go, oh, that's an integration by parts. Cool. You can kind of see it's a reversal of product rule. But if anybody wants to learn it, in the class, they go, show me. Take probably 5 minutes. You go, oh, cool, learn another rule. All right, great job with this. Now, this is what we're doing next. Evaluate the definite integral. So how about a 0 and a 1? That means what's here? 0 and 1. So I'm going to put a 0 and a 1 on the original one. I'll put it over here. What was the original problem? Because I scratched stuff out.
It was x e to the x squared.
All right. So if you wanna write this again in your notes, because I know a lot of you are now saying, oh, no, it's an definite integral, you got this, right? I'll be honest with you, I can't put these here. Or in fact, you know what? To really help students see this, make this a 2. This is the first time we're doing this, I shouldn't use 0 and 1. How about 0 to 2? Now this is important. I don't think I caught this as a student. What variable is this? dx? Everything's in terms of what? This is called the lower limit, this is called the upper limit, right? These are x values. So I want to point out, we never write it. This is really x equal to a what?
0,
We just never write, and this is x equal to a
2,
2. It really is. So those are x's. Well, I changed these to what letter?
u,
So I can't put 0 and 2 here, because these aren't x's anymore. What letters are these?
u's.
U's. So, what can you do? Here's my first suggestion. Most students take this option. You go, then what do? We got to evaluate this thing. Well, this had a what? 0 and 2, x's. This is x equal to 0, x equal to 2, right? But this changed to what letters?
u,
U's. So here's my suggestion. Most students decide to do this. Don't write them here. There's numbers here, just don't write them. There's numbers, that's you, just don't write it. But when you finally get to step 5 where you what? Resubstitute and you get it back to what? X squared, then you waited. You don't put the plus c because it's a definite integral, and you put your vertical line, and what numbers you put down?
0 and 2,
0 and 2. Because what letters are these? These are
X.
what?
x.
I mean, does that work?
Mm-hmm.
Yeah. So most students do that. They go, okay, I'll just wait. And when you finally get to resubstituting, then you get to put those original numbers down. Does that make sense?
Mm-hmm.
But I will show you what those numbers are. I gotta show you that, because some of you may like that. Okay? So Josephine, go ahead.
So when you put it back on, what you plug those in?
That's right. Because it was an original definite integral. And this, the beauty of this, Josephine, this is the one you can check with your calculator, right? The calculator doesn't do indefinite integrals, but it does what?
Definite.
All definite integrals. So we'll be able to check this. All right, I'm gonna put, but it's gonna put in decimal form. Go
Are
ahead.
you gonna subtract them?
You got it. I'm gonna put the 2 in here for x. Then I'm gonna put the 0 in here for what letter? X. But we never put the x equals, do we? We just put a what? 2 and 0. But don't, everyone, if you wanna put x equals, you can. Okay? My Calc 3 students, when it's x's and y's and z's, I have them doing it. X equals 0, y equals 2, etc. So substitute this. What's 2 squared?
4,
E to the 4?
Four. Mm-hmm.
Then you said it's a subtraction. E, so far so good, Josephine?
Mhm.
What happened to the plus c?
Remember what you said about definite integrals? Remember from last class? You could put it, but what's going to happen every time on a definite integral? The plus c's will just what?
cancel out.
Subtract out. So we say we don't have to put plus c if it's a
Definite.
definite integral, so I don't need that there. You could put it, but it would just subtract out when we do the subtraction. You only have to put plus c on what type? On a
Indefinite.
indefinite integral. Question, should I take off if someone forgets to put plus c on the test?
Yes.
Let me hear it. We'll take a vote.
Yes.
Take off if they forget to put plus c?
No.
I know, they're like, I know, it's gonna happen, it happens at least once, dude. You just forget to do what? You can probably catch me on the word. But this, we don't have to write it. Now, 1/2 e to the 4th, let me finish this up. 1/2 e to what power?
0, which is 1.
What's anything to the 0 power?
1.
So in my final answer, this is an exact form. I would leave it like this on the test. 1/2 e to the 4th minus
Half.
1/2. Or if you want to factor out the half, you could write it as what? I don't put it or. If you're a factoring type of person,
E to
you
the
like to factor a lot, then you'd have to do
e to the
e to the 4th.
minus 1.
And if you, the TI Inspire usually writes it like this, factored. You don't have to though, Josephine, you can do it like this. The calculator though is going to put it what? Decimal, this is called exact. This is the exact value of the integral. The calculator is going to give it in decimal format, you know, approximately.
Did you take points off?
Yeah. Oh, but hey, hold up. Let me be careful. I would have to on my exam say find the exact value, right? Right? If I didn't say find the exact value, if I just said evaluate the depth, you might have been like, okay, I'm going to evaluate it. Hey, I wanna show you something. What would go here? Cause these were really what letters?
You just plug in the limits from previous and period.
Outstanding.
So-
Everyone, if you wanna put the numbers here, if you're like, no, I wanna put those
So
numbers,
root
they
here.
have to be what letters? They have to be U's, right?
Uh-huh.
So here, let me write it. U equals, I wanna write it because I want you to point, these are U values.
So,
And you have to go over to this thing. Remember
So-
where you did your step one?
uh-huh.
And you gotta put a 0 in here to see what your new U is for the lower limit. And you have to put your 1, no, it's a 2. You gotta put your 2 in here to see your new limit. So, and what is 0 squared?
0,
But this won't be 2, will it?
4,
2 squared is a,
4,
now do y'all realize why I didn't use 0 and 1? Because 1 squared becomes a what?
1.
1, and student wouldn't make the, you wouldn't be able to see the difference between. Does that make sense?
Mm-hmm.
So, you know what that means? If you put this, and you like to do that, okay, then you could be really cool. And here, you could stop here. What numbers would they be?
4 and 0.
4 and 0. If you like that, and you wouldn't have to do which step. But I'll be honest, when I grade, I always try to see how many students do this. Not many do this. Most students do what? They just wait, resubstitute, and then put the original what? 0 and 2. But I want to point this out, that it's, you could do this, and then you just, see how it's U now? And you change the what? You change the limits in terms of U?
Mm-hmm.
What would you get? You still get the same answer?
Yep.
You sure do. Now that's your option. Isn't that cool? It's your option. Did you want to do that? When I grade, most students do what? They go, listen, I'll just use the original X's, I'll get down to the end, I'll resubstitute.
No, but that is more neat.
See, he likes this. He likes this. He'll probably do that every time. He'll change every time, he'll look to see what the new limits are. Okay? I was talking about those AP exams. They used to always create a math problem, not every year, but a lot of times, where they forced you to understand that concept. They would design it in a way that is like, they make a multiple choice. Which ones would these be if you wrote it in terms of you? They do that at the academy too. The mids at the academy, they get a common final. A lot of times they design it that way. So, but unless you wanted me to, no. I give students the option. Everyone gets. I just in class, I want to make sure you're aware that you can do it which way. No, Raj, I'm curious. Which way do you like? You have an option or a preference?
Not really.
No, he goes not really. He'll see. When he does a problem, what he prefers to do. Cool. So that's the idea. You could have changed these because what were these letters?
U.
These were U's, so you can go, I can get the answer right now. And you might find that easier, you won't have to resubstitute. I was trying to hold.
I mean, if you do the substitute, it's less work.
Yeah.
I like
Good
the
point.
I like the lazy way.
All right, one. Give it a shot. I hope you notice patterns to these. Let me go over here. What was the interval of e to the 2x again?
Half of e to the power 2x plus c.
I am hoping a lot of you do spot patterns to these. All right, Amber, good luck. What do you think?
U equals to 5x.
It's like you're already experts. What do you think we'll let u equal to? And do you notice we need substitution rule? Yeah, it's not just sine of x, it's sine composed of 5x. So, we'll let u equal to what?
5.
All right, what's step 2?
Du equals
du equals, what's the root of 5x?
5x equals 5x.
Put the dx here.
Mm-hmm.
Josephine, step 3. What do I do?
Divide the constant.
Yep, I'm gonna divide by 1/5 du. I wanna do this so I know I can get rid of all x's. No variables came up, so I just got this dx. Which things do I substitute?
U and the dx.
All right, I'm gonna keep doing this till you get tired of me going in here and going what? Woo, bye-bye. What's that become?
U sine of u.
That's a u. The sin stays though, right?
Mm-hmm.
The sin stays. What replaces the dx? That third place has a box. See? That box. What's this coming in and doing what here?
1/5 du.
You're gone. 1/5. du, that looks sloppy, where do I put the 1/5?
In
The front.
Man, you're good. Sine of u. Du. See, I'm happy. Do you see any x's left over? If I had an x left over, I'd be in trouble. That means I didn't do this properly, or it's not possible to do substitution rules. Sometimes it's just not possible to do it.
Now you can get
Like
rid of
e to the x
the,
squared.
get rid of the s.
Yep, now let's go over here. SCS. Which way are we going? That way, derivative or anti?
Anti.
And I put the negatives on which one?
Third and the fourth.
Third and the fourth. Right, Amber? We're doing antiderivative, so what's the antiderivative of a positive sign?
Negative cosine.
Negative cosine. Right?
Yeah.
All right, so negative 1/5, put it in front of that 1/5. Sine of u, is this a definite or indefinite integral?
Indef.
So let me change my directions, that's an indefinite integral, evaluate the indefinite integral.
What happened to the 5?
Oh, you're the best. I meant to do that.
She got you, Joseph.
Thanks, Josephine. Hey, do I have to put a plus anything?
Plus C.
Plus C, oh, don't forget because it's indefinite. Now look over, you're about to turn in your test next Monday, you're about to turn it in. Look at that carefully, did you forget anything? You. Yes, yes, good job.
5x.
Resubstitute. This was an indefinite integral, so cosine of. So Salmon, outstanding. He's
But
like,
you
hey,
don't
don't
need the
forget that.
c, right?
We
You
need
do
an
need the C.
indefinite integral. Plus constant, it's the
When
antiderivative.
do you need the c and when do you not need the c?
Plus C when it's indefinite, you need to plus C.
Indefinite.
Yep, right down. She's gonna go, I need to put plus C when it's an indefinite integral.
You see when when you see that S thing, if there are two numbers up, top and bottom, you don't need the C.
Don't need it.
Oh, when you had the two numbers on the top and bottom, then
Yeah.
you don't need the c.
C.
Yes. You got it. Hey, how can I check that?
You can take the derivative.
Love it. So if you ever wanted to check any of these, take the derivative. You gotta do chain rule. Go back to that. This is the opposite of chain rule, right? Cool. All right, let's try another one. I like to build this slowly, if you don't mind. Slowly, because you rock and roll, you hit anything. If I start throwing exponents like x squareds and x cubes, I think you're gonna notice what's gonna be the power difference.
1.
1. So check this out. Okay, I'll use cosine. Well, then that's how I have to set it up. I know. Oh, wow. X to the fourth and x cubed, huh? X cubed and x to the fourth. No, we'll be good. But Josephine, I do want to point out, when I set this up, did you notice my power difference? X to the fourth, and this over here is what? X cubed. You'll see why. Because guess what you're letting u equal to? The one that's higher by 1. Oh, the thing in the parentheses. All right, step 2, differentiate. Now, what is the derivative of x to the fourth? 4x cubed dx. Josephine, step 1. Step 2, right? Good. Step 3, I always divide out the what? The number.
Constant.
Yeah, divide out the number. Very good. I'm going to just divide it. So it'll be 1/4 of what? But look at this. Amber, look what I'm leaving with the dx, the x cubed staying over here with this. All the x's are staying over on this right side. I just divided that little 4.
Yeah.
Substitution time. Let's rock and roll. Where are you coming? What's that? Yeah. See, everything, all the x's have to go away. Well, what's replacing the x cubed and the dx? So look, you're out, and you're out, and I'm putting in place of it a 1/4 du. So, any suggestions about the 1/4? Now you got a clean integral. What's the integral of cos? Positive sign. Plus Charlie, because there were no numbers.
Mhm.
And don't forget to resubstitute. What
So
was u?
wherever there's u, you make it an x.
Oh, but look what we let u equal to in this problem.
Oh, x to the fourth.
There you go. 1/4 sine of, and I could check this, couldn't I?
Also, this is the same thing as the E, just, also, this is the simple harmonic motion, right?
You got it.
That's what they
What
call?
was the original question, problem
Oh, evaluate the indefinite integral.
of what?
And it was, I'll put it over here. The original one before I crossed everything out. Yeah, I'll put it right next to it. It was the integral of x cubed cosine of x to the fourth inside the parentheses dx. Okay? Josephine?
Do you ever get a power difference of more than one?
Well, so I can be careful. It's like, not on these, because what you could tell what would happen. It wouldn't what? It wouldn't work, because this step we just differentiate, and by power rule it goes down by. But now sometimes we get trig functions, okay? Some things don't deal with that. Trig functions, logarithmic functions. So before we leave today, we'll do some logs, right? But yeah, you're right. Now, are there other techniques out there? Yeah. One of the hardest though, Josephine, was that flat out e to the x squared alone. Substitution rule doesn't work. Yeah, x squared versus just nothing there. So mathematicians kind of went, what are we going to do with this? Now think about it. What can we fall back on? If it was a definite integral, we could go back to Riemann sums and set up like over the integral, and if like 1,000 rectangles underneath the curve, and we'd probably be accurate to about 8 decimal places or so. You know, that's what I mean with in terms of your career, where you're going to be like, oh, okay. I can approximate it to 8 decimal places. That's good enough for me. If there's no technique of it. All right. Taking it slow, Here you go. By the way, I keep writing 5-4. I'm sorry, this is 5-5. This is substitution rule. All right, this one's going to be interesting. Because it may look like product rule, but it's the reversal of it, of the chain rule. This is substitution rule.
So always take the one with the higher power, right? So if it is secant
know.
square x, right?
So in here you and I are looking at this. 10x times what? Secant squared of x. We don't know what to let u equal to, do you agree? But it's obvious this must involve, it's a good possibility this involves the substitution rule. You go, why? Because that's the only rule we've learned so far. Okay, yeah, but it's not just going to be something alone. So when I've got this tan x times secant squared of x, and I'm trying to integrate this, I got to let u equal to something. So how about you and I think about the trig functions and their derivatives. I'm going to go way over here. I got the SCSES. And what's the derivative of tangent of x?
Secant square x dx.
Aha. This is going to help us. Our knowledge of that. You go, why? What I'll do is, over here, I'll let u equal the tangent of x. I'll let u equal the tangent of x. And you go, why am I doing this? You know? By the way, if you tried something and didn't work, you just try again. I'm going to let u equal to tangent x because I have knowledge of trig derivatives. The derivative of tangent of x is secant squared of x. Do you follow me?
Mm-hmm.
So if I do this, what happens in step 2?
Du.
Who else emerges?
Du.
That other piece. There we go. du equals secant squared x dx. Cool? Now, when this is the first time this is happening, Josephine, you asked about this earlier. I don't see a constant. Oh, it's a 1. So do I really have to go to step 3?
No.
No. This is the first time that's happened yet today, but you're like, I don't have to go to step 3, right? Because there's no what? 2 in front, or 3, or a 5. It's just an invisible what? 1. So when I do my 2 boxes to substitute, u and, well, this didn't have to occur, so I get to use that one. So sometimes you get this done in 2 steps, not always. I didn't go to step 3 because I didn't get this what? A 3 over here, or a 5. So I'm going to go right now. Here we go. What's u equal to? U becomes, so I'm going to take out the entire tangent of x and put what?
You.
U. Now what's this? I love this part. What's du remove?
Secant square.
Everything else. I love it. You okay? Make it easier on us here. Bye-bye. Even that squared. Du. So let me write this again. Now the integral of x is x squared over 2. Bless you. So Arjun, what's the integral of u? It'll be u squared over 2. Oh, indefinite integral, no numbers, plus what? I'll look over it again. You're about to turn in your test. Does that look okay, or did
No.
I forget something?
Tan squared x over
The original problem had what letters? The original problem had the variable x in there, so I'm going to have to go back, and what did I let u equal to? Tan of x, so I'm going to have to write my answer like this. Now, can I show you how the back of the book likes to write this? Who in here likes to use this notation? They put the little squared there. Do you like that?
Yeah.
You could do that. Did you notice the textbook likes to do that? This, they like to write like this because it's less symbols. You don't have to though. You don't have to write it like that. That means this, but the textbook does this. They put the little 2 between the n and the what? Yeah, so how do they write this? You've seen it before. I know you've seen it before. We did it when we were doing derivatives. They write this as what? Yeah, they write it like that. Just a little bit easier, right? Less writing, but you don't have to. It means the same thing. So it
So
eases.
like tan square x is like tan x times tan x, which is right.
That's right. Heck, you could write tan x times tan x over 2. Let's see. And you can start using trig identities if you wanted to. It would be sine squared over cosine squared.
Yep.
With that 2 down there. Yep. Yeah. If you wanted to. Sometimes I'm about to mark something wrong and I see a student did a trig identity replacement for one of their answers. I'm like, oh, okay. They wanted to write the answer in sine and cosine. Okay. So that's what I mean. This is called an antiderivative. So there's other ways you can write antiderivatives because of the trig identities. Does that make sense? I mean, this problem alone, I think there's 3 ways I can think of you can write that answer. See, when there's options here. Josephine, like what would you let u equal to? There's different ways to do that problem.
Any of them.
U equals.
That would work.
I would
There's
do
other options. You know why this works? Because what's the derivative of sine?
negative.
Cosine. But you could have used u equal to cosine because the derivative is a negative one. Sine. So it's funny that this would work. But I'm going to use your suggestion. So u equals sine, u equals sine of x, du equals cosine. No constant. Stop here. What's this replace?
Sine of x.
Du. What replaces the cosine x dx?
Du.
Du. What's the integral of u? Du.
Half u squared over 2.
U squared over 2. Plus Charlie, right?
Mm-hmm.
If you made u equal cosine, would we have to make the whole thing negative?
Yep. So it would give a different answer, wouldn't it? But I want to tell you, these antiderivatives, they'd be equivalent. You go, why? Because of the plus c. So I would have to make an answer key, Josephine, for the different ways people wrote the answer. So what's one way to write this answer? U is what? Plus Charlie.
Mm-hmm.
Plus Charlie, plus C, right? You could put the 2 like right there if you like to do that. But obviously, if we used u equal cosine, this answer would have had a different answer, but both are okay. There's different ways to write the antiderivatives. You know why? Because of the plus what? Plus C. That's why. But when it's definite integrals, no matter what, you're going to get the same definite answer. That's the beauty of mathematics. Cool? All right, try another one. We haven't seen any fractions yet. All right. I think I'll use 2. And when sometimes the author likes to use a y. Okay. I know. Might as well do it. Sometimes the author likes to use what letter? Y, or T, right? Okay. By the way, could you just start the problem and say y equals x and change them all to x's if you wanted to? Yeah, feel free to do all x's, that's okay. I bet you all know what to let u equal to. A lot of times it's the thing in the exponent, or a lot of times it's the thing in the parentheses. But when there's a power difference, it's the one with the higher power by 1. Well, this, I don't see like a power difference, but I see something in the parentheses. What do you think I let u equal to?
2y plus 1.
You nailed it. Okay. Composite function. du, now what's that derivative? 2, I gotta put dy, everyone, right? 2 dy. Now, Josephine, I will have to do step 3 because I got this 2 to pop up, huh?
1/2 du.
Or do I have to? I'm gonna do it, but watch, I'm gonna fall back. A lot of you are gonna tell me, hey, professor, you could have stopped at step 2. So I'm not out to confuse anybody, but Josephine, I'm gonna follow my what, step-by-step method. I see a constant, right? And I said this works every time. If I get a constant, I do what? I divide it. But after I do this, I want you to look back on it and tell me what you think if I could have stopped there. So I'll take this 2, and I'll do that. Now what's this 1/2 du replace? Now I'm gonna put the original problem over here. 2y plus 1/6 dy. Alright, what's this 1/2 du replacing? 1/2 du. That 2 stays. That's a number, it stays. But what replaces this 2y plus 1? U. So let me write this again. There's a 2 up there. Where can I put the half? In front. Alright, 1/2 in front. This 2 is sitting up here in the numerator. And I've got a u to a 6 down in the bottom. Alright, I'm sorry, and then I got a du, right? Now, I think you all know this. What's 1/2 times a 2?
1.
So shouldn't we do that right away? I mean, think about it. We all can see this. What's 1/2 times a 2? Just a what? 1. So let me write this again and just put 1 over 1. Y'all see that? Right? I can multiply that half to that 2. So Josephine, I didn't want to confuse you or anybody, but I want you to see something. Doesn't that mean, see the original problem? Doesn't that mean if you wanted to, those in this class who are really good at this stuff, you might have looked at step 2 and said, oh, I could have stopped right here, and I could have replaced what with the du in the original problem? The dy and the what? 2. Do you see that? You might have done that. So Josephine, I always just go to step 3, divide the constant, but you might observe it and go, well, hold up. 2d, this had a 2 already, and a dy, might as well just replace that with the du in step 2. Like Belrash, feel free to do stuff like that, right? Sometimes you can stop at step 2 if you got, this is already there. I'll just replace it with a du. But we'll get it anyways. Now, how do you do these integrals? There's no quotient rule.
-6.
U to a -6. Now ours, remember here we're talking about this, you gotta pump this up by one integer and then divide by that number. The only thing is be careful with the number line. If you take -6 and you add 1,
-5.
-5. Alright, so here we go. This becomes u to the -5 over
-5
plus
plus
c.
c.
Now what was u?
2y plus 1.
So u was 2y, so I'll put my parentheses back, see? To a -5 over
-5.
plus c. You might prefer to write this in this manner. When you write final answers, it's not the best idea to leave negative exponents in your final answer. It's good to write your final answer with positive exponents, so how could I write that?
-1.
Big 1 in the numerator. There's a -5 here. I can put the negative in with the 1 if I want. I'll keep the 5 here, and then next to this 5, I'll put 2y plus 1 to a positive 1.
Can we write fifth root?
And you go like this. But, yeah, if you were wondering, would I accept that? I would. Because it says, evaluate the indefinite. It didn't say anything about don't leave negative exponents. But I think it's good to do this because a lot of times we are doing definite integrals. And isn't that easy if it said go from y equal to 0 to y equals 1? Right? Is that what I got this? By the way, we haven't done a definite integral in about half hour, so maybe we should do one. Ready? It's coming off. Amber, this is gonna have numbers.
So no constant.
0 to 1. What does that mean? What happened when I got all the way to here?
That means there's not gonna be a C.
And what can I put right here? That means right over here.
Oh, okay, so if there's numbers, then you just do that line and do
Now wait to the end, right? What goes right here?
just the line and then one.
And these were Y's, does that agree?
Uh-huh.
Although Art might change them and put the U's here.
Yeah.
He'd make the two new U's here, but I'm just gonna bypass that, keep waiting, get to the end. Here I am, I have to substitute what number? 1 for what? Y, then I have to substitute a 0, and then I have to do what with these? Subtract them? Alright, here we go. I went negative 1/5 times, what's 2 times 1 plus 1? To the 5th.
3 to the power 5th.
Oh, that's gonna be
right?
huge. Way to go, messenger. You
Instead of that, do
tough one to put numbers in.
that would have been easier. One over e to
See,
the.
Art's got a good point. We gotta do 3 to the 5th power. What's that? 243? Then we gotta multiply 5. All right, great. Hey, I'll get back to this. Now we do a subtraction, and then I put in what number?
0.
Right? Just always a subtraction. Then I put in a 0. Subtraction, negative 1 over 5 times 2 times 0 plus 1 to the 5th. Or when this is negative 1 over whatever,
12,
5 times
12, 12,
243.
15. 12, 15.
How much is that? 1,000?
12, 15.
12, 15. Minus
That is 5.
5 times 32.
No, not right. 2 to the power 0 is 0. Plus 1.
Yeah, so negative 1/5.
Negative 1/5. Yep.
Now when I subtract these, I have to do common denominators, don't I?
Yeah, so I can do that for you. 1.
And want to do it for me? Or read the best?
Yeah.
I'm just gonna subtract these.
1
I could have common
over
denominators.
5th.
Shouldn't it be as
It
So.
should be a positive.
I love it. Everyone,
Oh,
I
sure.
did that on purpose. So thank you. See the negative?
Yeah.
Kel, who else saw that? Very good. Kel saw it. I heard some other voices. Thank you. This minus makes it a what?
Positive.
Ah.
That comes to 242 over 1215.
Thanks, Art.
No problem.
Hey, could you check any definite integral with the calculator? Can't we? Can't we check every with the TI 83 and 84?
Yeah.
So you can check that, right? Oh, good, she snapshot.
I got video camera.
Josh, you get it?
Yeah.
Oh, that's good. Evan, did I do a secant with a tan earlier?
Yeah.
Yeah.
Here's a tough one. Give it a couple stars. Toughie. You know why?
Secant cube x.
Because what's the derivative of tangent? So you and I have to figure out some way to do this problem.
We can do it. You can do
Well, we can do it.
secant square x times secant x. Divide it like that.
Yeah.
Factor out of secant x.
Yeah.
Make a u substitution for secant x.
I like this. I like the way you all are thinking. Everyone, how about this? We know the derivative of tangent is what?
Secant square x.
Secant squared, right? But daggone it, it's a secant what?
Cube.
But can't we rewrite this? This is what I'm hearing from everyone. Can I think of this as tangent of x times a secant of x times a what?
Secant square x.
Secant squared of x. Can I think of it that way?
Uh-huh.
Right? Can I do it that way?
Yes.
Now, if I let u equal tangent, it doesn't work. And I want you to see why. But don't get too worried about it, okay? Watch this. Let me put my sad face on. This isn't gonna work here, and then I'll get your question, Josephine. I'm playing around with this, trying to figure out what to do. Do not think the first time you see this, it should just come natural. Because we look at this and we go, you know, you try something, right?
Mhm.
Now you do a substitution rule. Josephine, I'll get your questions up, and I'm like, I'm just gonna try something. I know about this, right? I know about these. So I'm just gonna think, well, that's that. But I noticed this isn't gonna work because when I get here, all I get is the what?
Secant square dx.
And I notice when I go substitute, I'll be able to knock that out, I'll be able to knock that out, but what will still be sitting around?
Secant x.
So does anybody know another relationship with secant and tans with derivatives?
Isn't there one that has it as tan x secant?
Oh, you nailed it. What's the derivative of secant of x? Secant what?
X tan x.
This is gonna get us through this problem. And when we're like, we know that the cotangent, cosecants don't come up too often, but we know the derivative of secant is what? Holy cow, everyone, what if you look at these together? Maybe I should write it that way, here. Can we write it that way? Let's write this as secant x what? And let's write this thing like this. Oh, this is gonna be a piece of cake now. It wasn't working before. And don't worry, that's the fun part of math. I tried something, it didn't work, Amber. Well, let me try something with the secant tan. Remember I tried to let u equal tangent? It wasn't gonna work there. Tangent cubed, it wasn't working. But now I looked at this like this. And I'm like, what if I just let u equal who? Now don't say secant squared. That'll get too complicated. You secant squared, you're gonna get a crazy product rule up here, or chain rule. We're just saying, just let u equal simply what?
Secant x tan.
Secant of x. Your u is usually something really simple. Now what's that derivative? X tan x. Dx. And when there's no step 3 this time, is there? So what's this gonna replace? That's
So it
gonna
is
knock out the...
secant x tan x and dx.
Yep. So when I'm gonna go in here we go. This is replacing the what? What's going in there?
U.
U?
Mhm.
But the squared stays. Don't agree? This is just replacing the u, okay? No constant, so I didn't go to step 3. What's du replacing? The secant x,
tan
the
x,
tan x, and the
dx.
dx. And I'll just put down a simple du. So let me write this again. I've got an integral of a u squared du. We got it. What's the integral of u squared now? U to the 3 over...
3.
Yep. And then put your u back. What was u?
Secant cube x.
Now, are you one of these that likes to put the cube here?
Mm-hmm.
Remember, you can do, oh, good. You like to do it. The book, you can do that. It all, or what's another one?
Secant x whole cube.
Cube. I get worried when I just write it like this, students think they have to, or they don't make sense of that. These mean the same. What do y'all think? Not bad, huh? Don't be afraid when you try something that doesn't work. You go to another option, right? Cool. Hey, let's do another one with a fraction. Let's jam a radical in there. Sound good?
Okay.
All right. Fraction, we're gonna jam a big radical in there, and you're gonna tell us what to let u equal to. Now here, you go. I don't know. Sometimes you don't know what to do. Some suggestions. Sometimes it's the exponent, or it's the thing under the radical, or it's the thing in the parentheses. And when there's power differences, it's the one with the power difference, higher power by 1. And when in doubt, just try something, right? It doesn't work, try something else. All right, here you go. How many is 5, 5? Let's just throw some crazy radical down here. Can I use t?
Mm-hmm.
All right, t cubed. Let's jam some big radical down here. Let's stick this to the 4th power. No. 6th power.
Okay.
Crazy 6th root, right? And then for this part, how about 1 plus? T to the 4. This thing looks crazy. So u sub, what do you think we'll let u equal to?
1 plus t 4.
1 plus t to the 4th. It was the thing under the radical, right? And sure enough, what's the derivative of a t to the fourth?
4
4t to the what?
cube.
And I'm not so worried about the 4, but you'll get a t cubed, which is going to knock out the what? Do you see how I set up this problem? You saw me making up. You see that? I made sure when I was setting this up, Kayla, I was like, I'll make that power difference with that one a difference by what? 1. I wasn't worried about that thing. I wasn't worried about that at all. That could have been a 12. That could have been a square root. Okay, but I was making sure when I designed this for the class, for learning about substitution rule, on purpose I made that a target by 1. So we go off to the side, u equals 1 plus t to the fourth. Not just t to the fourth, the 1 plus t to the fourth. All right, what's du? Good. 4t cubed d what? dt. All right, step 1. Step 2. The other students who can do all this stuff in their head. You go, which students? Probably you. You'll probably get to the point where you get tired of writing this every time. I'm serious. You'll be in Calc 2 and just go, in your head, you'll kind of see all this happening and you'll go back in and change everything. I'm serious. Step 3, I get a constant, I'm going to have to what? All right, 1/4 du. t cubed dt. All right. What's getting replaced? That's wrong. Good job. U's coming in for the kill. Bye-bye. You just what letter? But this radical with the 6th root there stays. What's this 1/4 du replace? And we'll replace the t cubed and the dt. Alright, then you're out. 1/4 I'll put here, because it just felt like it. And dt there. Now right away, where do we put this 1/4? Can we do that? Yeah, shove it out of here. 1/4. Way out. Get it out of the way.
It's du.
Oh, it's a D. Oh, DU, you're the best. Thank you so much. We changed T's to be U's. So I'll put the 1/4 there. I'll keep the DU off to the side. I've got a 1 now in the numerator, but this 6th root got really small now. This just has what little letter? Now, how do you integrate this?
1/6, t to the power 1/6.
Yep, we put it back to exponential form, right? Yeah, that's u to a 1/6, and if we bring it up to the numerator, u to the negative 1/6. So of course this answer is going to look bizarre, because when you add a 1 to a 1/6, negative 1/6, excuse me, negative 1/6 plus 6/6 is what, 5/6?
5/6, yep. And you have to
Here we go, let's be careful.
6
1/4 u to the 5/6. Ours, here I go, I'm dividing a 5/6, but divide 5/6 in math means
reciprocal to 6/5.
multiply the
6
reciprocal 6 this
So that,
times 1.
that becomes 3/10.
Oh yeah, because 6/20. We can reduce that, huh? Right, 6/5 times 4, 6/20. We can reduce that to be 3/10.
Mm-hmm.
Right, everyone? And then you get u to the 5/6
Let's see.
plus c. Now, don't forget, this was an indefinite integral. Amber didn't have numbers. I got to put the resubstitute, right?
Yeah.
And I have to put the plus c. What was u?
1 plus 2, 4.
So here's the answer. 3/10 parentheses 1 plus t to the 4th raised to the 5/6 power plus c. You could check this by differentiating it if you wanted to.
Can you show some IBP, integration by product?
Oh, heck yeah, I'll show you that.
Okay.
I gotta show you that, everyone. I gotta show you that one. Oh, go ahead.
Where did you get the 5/6?
So once the hard mark was over here. So 1/4 integral u to the negative 1/6 du. Now we do the antiderivative. You know the rule. You pump it up by one integer, divide by the number. But what's negative 1/6 add 1? Oh, common denominators. Negative 1/6 plus 6/6 makes it 5/6. And then we gotta divide by it. There you go. Hey, if you have to, Students sometimes pull out the calculator, what the heck is negative 1/6 plus 1? They frack it, you know, just to make sure. You can do that. Isn't it weird? So Art, I'm going to show you that one, but I got a new one. And when we, in this class, know how to take the integral of sine, don't we? We know how to do the integral of cosine, don't we?
Mm-hmm.
Yes, you do. What about this guy? Some of you might say secant squared. That's what I did in my, I remember I was a student, I screwed up and did that. Wrong. I was the guy, I had it backwards. Knowing the derivative of tangent is what? Secant squared, so the integral of tangent, not secant squared. We haven't seen this yet. I haven't shown it to you yet, but we can do it now. But we gotta put our thinking caps on, okay?
Mm-hmm.
So when we're gonna put our thinking caps on, all right? Now don't forget, let me put something over here. What's the integral of 1 over x?
Natural log of absolute value of x.
Natural log, you gotta put an absolute value of what?
X.
Is
Plus.
that what I agree?
Mm-hmm.
Don't forget that. What's the integral of 1 over x? Natural log of x plus c, true? Let's have some fun. This is the first time we're doing this. So this is fun. When we're finding the antiderivative of tangent x, we haven't done that yet. Believe it or not, it involves a use of. Yep.
Also, that
We gotta put our thinking caps on here, because look. I mean, I got my u ready. I've got my du ready. Everyone, we're looking at this going, what the heck? What, are you gonna let u equal tangent? You're gonna go nowhere, right? Okay, maybe I'll let u equal x. We're gonna go nowhere with that. And what's the derivative of x? 1. Yeah, that's not gonna work. But we're gonna get this. We just need to back up and remember a very important trig identity. Who? Raise your hand. Who knows a very, I call it a 5-star trig identity. A trig identity for tangent of x. What do you guess? Sine over cosine. That's going to get us through this problem. You know why? What's the derivative of sine?
cosine.
Cosine. Or if you want, what's the derivative of cosine? Sine. So here we go. To get this problem rocking and rolling with the what? Substitution rule? We know we got to get something to kind of cancel out when we do this. And substitute. We're going to start out by saying this is the same as, we use the trig identity. But there's no other way to do this problem. That's how we got to do it, right? That's why that trig identity is so important to know. We got to know that one. By the way, who has one for cotangent of x? Cosine over what?
Sine.
That's what you do. You do the same thing. Now, this, don't get upset. Don't get upset, everyone in here. If you try this and you screwed up at first. Because right now you might think you have an option, but we don't. We're going to let u equal to sine or cosine. One of them works, the other one doesn't work. So don't get worried if you try it and what? Doesn't work. So maybe on purpose I should try the one that doesn't work. I want to show it to you. Watch this. Ready? This would not work. I want you to see why. Let me get my set, even this isn't going to work. You why? It looks like it. Sine and cosine. Well, what's the derivative?
Cosine x, yeah, you don't know what.
Okay, now watch this. Go substitute. No constants, right, Josephine? I want you to see why this doesn't work. There's no constant here, is there? Right? Alright, so now I get ready to substitute. Well, the u will replace the what? The sine, right? Oh, cool, cool. Alright, you're gonna be u, but sorry. It doesn't match up. Du must equal what?
1 over x.
Cosine dx. Dx is not the same as 1 over cosine dx. You see what I'm saying?
Mm-hmm.
Well, no worries. Change this upside down frown to a happy face. I'm going to try and let u equal what? What's my other option? Cosine. Oh, it'll work now. So just remember that. Do not fear when you try and it doesn't work. Just scratch it out. Just go, hey, let me let u equal the other one. I've done it many times. Oh, whoops. So let u equal cosine x. Now what's that? Be careful. Because we keep doing antiderivatives and derivatives. We get confused. We need this. True? What's the derivative?
Negative sine x.
Is it negative or positive? Look, we're doing derivative over here. When we go off to the side, we do derivative. Derivative of cosine of x is
Negative sine
negative sine of x
dx.
dx. Josephine, a negative popped up. So that's a constant, isn't it really? Right? Isn't it? -1? So what can I do? I can divide a what on both sides?
-1.
Well, this looks silly when if I divide a -1, so you okay if I just write it as negative du?
Mm-hmm.
So here, I'm gonna write this. Negative du is equivalent to the what?
Sine of dx.
Let me box these. This is gonna work. This is gonna work. Let me get this set up again. Keep in mind, this would work for cotangent as well. What about secant and cosecant? Wait till Calc 2. Don't worry, we don't give you those. Alright, let's go in here. What you replacing? Ooh, down here. Look at this, everyone down here. Right? U's down there now. Now, what's this negative du replace? Yeah, it's going to replace the entire sine of x dx, right? Here we go. Cross out this and put down what? Now, when I've got, don't forget my little negative, right? Where can I put the negative? See, that's what happened. The negative just stayed up front. Now, look carefully at that. That's not negative integral of u. What's in the numerator?
1 over u.
Everyone see that?
Mm-hmm.
Right? Now we're over here. What's the integral of 1 over x?
So negative
Natural log of what?
u.
X, right? Negative.
Natural
Natural log. Here we go. Natural log.
cosine x.
Now, if you want to be fancy, does anybody know a rule? There's only 3 log properties where you can move this to the power.
Mm-hmm.
Did you know that? Did you know you're allowed to do that? So I should put in more here. This is for all you nifty, know your log properties. I could write this as ln of cosine of x to what power?
-1.
Now, at cosine of x to the -1, that doesn't mean inverse cosine, it means 1 over cosine. What is 1 over cosine? What's 1 over cosine? That's not inverse cosine, that's just...
Secant.
Yeah, that's 1 over cosine. So, if you want to be cool, you can write this like that. Do you have to, though? No, this is fine. This is fine. Don't think you got to do that. All right? That's totally fine. But if you want it, if you notice, you can put that negative and kind of move it up here. Just keep the bars around it, right? People get confused, or they think that's the actual antiderivative. What do y'all think of the U stuff, huh?
Excellent.
Guess what we're doing tomorrow? More of these. This is like related rates. It's the one class I like to spend. I like to spend 2 classes on what? Substitutional. I am telling you, it's the main rule used in Calc 2 and Calc 3 for anti-differentiation. Okay? And I get students all the time, especially down at the Naval Academy, I have to edit that, but I get them, Calc 3, they can't do U subs. And I'm like, first day, I'm like, okay, let's review U subs. Do this a couple times. So great job. Have a super day, and Art, before you leave, I'm going to show you what.
IBP? Okay.
Cool. Kaylee, you like this stuff? Oh, cool. Kelly, do you like this?
I mean, the first song you did, that's gotta be 1/2.
You knew.
No, but that's why I smiled, because you take the derivative of either 2x.
See you, man.
Good call. Good logic.
Tomorrow we'll go over more of these.
A bunch more.
And then Thursday,
You got it. Does that work?
and then Monday we'll do the final one, and so either do it Wednesday or Thursday.
You nailed it. And don't hesitate. If this Thursday, if you feel pretty much confident with the anti-reading, just want to ask a question about something, that's great. I'll do it.
See you, ladies. Bye.
Okay,
I'm serious.
so just like go ahead and ask.
Final exams are weighted more than tests. And you might just say, hey, Thursday, I'm ready for this. I'm going to ask about that.
See ya. Have fun.
Okay? Josephine, so feel free to do that. Tuesday, we gotta review that. But hey, if you're, because I think a lot of you are gonna start
Yeah,
prepping
just
over
this one, 1 to 4, 4. That will be easy.
On Thursday, do I have to come in on Wednesday?
Because a lot of people like to study on their own.
Is everything
When you guys come to the like chapter 7 or 8, let me know. I can help you
More
out.
use
Those
of
are
it.
difficult.
He said
It's a good day to miss.
Who's it?
No.
He said chapter 5.
More and more use of it.
Chapter 5 is
Get
entropy.
notes.
Yeah, I'll get the notes.
Chapter 6 is what? Quantum mechanics. Literal quantum mechanics. Chapter 7.
In the morning for class.
What are you talking
I
about?
know.
Math 141, Reba. Reba, the one that was wearing orange this morning.
What's that?
Reba.
Ariba?
That's my sister.
I gotta remember
She
this.
wasn't gonna tell you.
How did I
about
not
that.
know? Is her last name
We
B-U-T-T?
have two different last names.
Oh, thank you. Because I would have caught that.
Yeah, no one can do that.
Ariba. All right, I gotta make sure, because I just started teaching them, so I don't have the names down yet. Does she like it, or is it boring?
No, she likes it.
Oh.
I told her you were a good professor.
Oh,
and
that's-
she was like, she likes the class.
Oh, cool.
Yeah. She just started doing practice problems, and I was just watching her while I had math right in front of me.
All right, Ariba, right?
Yeah, Reba.
It's your sister.
Yep.
Cool. Thanks.
Thank you.
We're here to learn the new method you were talking about.
You too?
Yeah,
let's go. Where's Art? Art, you gonna watch?
Yeah,
They wanna see it too.
I'll record it too.
Alright, Art. You gotta come up here with us.
Hey, you know what we gotta do first though?
What?
Can we prove it?
Sure.
Oh, he's gonna get on camera. We're gonna prove this thing first. Now let's,
You probably want to stand here with the camera.
let's say M is F times G, right?
Mm-hmm.
Now what's the derivative of that?
F prime
What's G?
G. The F prime
Whoa, what
G.
am I doing?
F
He's
prime.
tired.
F
First-
prime times G.
First time to the second.
Yeah. Plus G times F prime.
G.
I'm gonna point out that when we're done, people like to write this with U's and V's, okay? They love to use U's and V's for this. Now, this is derivative M, right?
Mm-hmm.
Okay, well, what if we integrated everything? And you integrate this right here. All right.
So the G prime will become G,
All right.
and F prime will become F, original function.
Same thing.
Integration, right?
Same thing, except with the F.
Hold on, let him think. Let him think.
Mm-hmm. And then when this was the derivative of an F times G, right?
Uh-huh.
So, if I call this, let's see here. I want to make sure we prove it. Because I want you to change it to U's and V's. Maybe I should use, before I show you this, this be, hold up. I want to use, I want to write letters.
Okay.
Give me a sec. You'll like this too. I'm telling you, it'll only take you like 5 minutes. The reason I wanted to show you the proof, because the proof kind of is cool, it's fast. You know, a lot of math proofs are what? Tough,
Yeah, yeah.
sometimes impossible.
When do you do these things, like prove by induction and all this? That's like for discrete?
Yep. All right. Here we go. And what's the derivative? So I think it helps when you write f of x and you write g of x. And what's the derivative by product rule of an f of x times a g of x?
So f x times g prime of x
Okay?
plus g of x times f prime of x.
Rock and roll. Awesome, everyone good?
Uh-huh.
Now, we're gonna prove this. We're gonna come up with a technique for doing the opposite of product rule. So let's integrate both sides of the equation. Well, the good news is, guess what happens when you integrate a d dx?
So f becomes fxg.
The good news is, when you do this with this, what happens to it?
It comes to the original equation.
You know, it's like square root something squared. It just does what here?
original equation,
So this just becomes what?
fx gx.
Coming back to you. All right, now, unfortunately, these both get integrals. So you get an integral of f of x, g, prime of x, plus an integral of what?
I see it right now.
He sees it.
So basically it will be
Right.
g of x with integration of fx
Yeah,
plus f of x integration of g of x,
yeah.
right?
And then if you want, you can call this dx here, if you want to think of these with like dx's, right? Because then they always put the dx there.
Uh-huh.
But now, what we're gonna do is, we're gonna write this so we get this isolated. So I need this off this side.
Okay.
So right now we have this, let me write it again.
Uh-huh.
Alright. I just wanted you to see the proof. So thanks for hanging through the proof. Alright, let's get this thing isolated. That'll be what the formula we've written as. So I have to subtract that.
Yeah.
So now you go, alright, the integral of f g prime of x
Mm-hmm.
dx is equal to, here it comes, this is gonna be our formula. This is gonna be our formula. We're gonna take that and subtract this. Alright, here it is. It's gonna be f g of x, subtract the what? Integral of g of x times what?
f prime of x
F prime of x
dx.
dx. Cool? Now,
Uh-huh.
that's hard to remember. So what we do is, in calc, we come up with letters U's and V's to make this easier to memorize, just to remember. So we're gonna let's go over here. Let's let F be the letter U.
Mm-hmm.
Let's let G be the letter V.
Mm-hmm.
So this means the integral of any U, that would be what? dv,
Mm-hmm.
we can say g prime of x dx, it's just a dv,
Yeah.
will always equal, here comes the formula, u v minus integral v du.
D, okay.
And this is the formula that you want to memorize. And so everyone in calculus goes uv minus integral v du. Now we're going to work a problem, and I want to do our x e to the x one.
Okay.
Will that work?
Yeah.
So we're going to use this to integrate x e to the x. But there's a formula, let me put it over here. It's called the integration by
Product.
parts. It's the opposite of product
Right.
rule. And we're saying the integral of a u, where is it, u dv, will
Uh-huh.
always equal u v minus integral v du. A lot of students say voodoo, like the word voodoo.
Mhm.
Some say ultraviolet. They come up with different phrases like University of Virginia and all these other things. Just to help them remember.
Right.
You know, UV, University of Vermont. I've heard it all. I've heard it all. So now, let's have some fun.
So we can, between x and ex, we can take any one of them as u or v, or that's.
Great question. You're going to learn from experience. But
Uh-huh.
I'll tell you, through peer, you're gonna go, what should I let u equal to in these problems? So everyone's gonna have to let u equal something,
Uh-huh.
and then we're gonna differentiate it.
Gotcha.
And then we're gonna have to look at this. This formula is written as in terms of u and a what? dv.
Uh-huh.
So we're gonna have to let u equal one part of this, then we're gonna have to let the other part be the dv.
Uh-huh.
So let me put u equals, I'm gonna put a box, and then over here, I'm gonna put dv equals a box.
Gotcha.
Now what I want you to do is, once we figure out what to let u and v equal something, u and dv equals something, we're going to differentiate that
Uh-huh.
to get a du. We're going to integrate that.
I remember this.
Oh, he got it. All right, so watch this. Now ours like, what should I let u equal to? I want to tell you, if it's got like x e to the x, x sine of x, x cosine of x, x times tangent, anything like that, let u be the x.
I had Kapoor for Calc 2.
Oh, you did?
Kapoor, yeah. So he's like really good with this stuff.
Oh, cool. And you had him for Calc 2?
Yeah.
So you did Calc 1, Calc 2, then you came back to Calc 1, or?
Well, Calc 1 I took in high school, so I was just like, let's just.
Oh!
I'm taking Calc 2 next semester.
Hey, cool.
I've taken DVQ also.
Yeah, or now you're gonna take it with him? Calc 2?
Calc 3?
I mean Calc 2.
No,
You take it with him?
I already took Calc 2.
So you wouldn't have to do it again?
No,
Oh, that's cool. That's awesome. Now, did you take it with him here at UMBC?
over here.
Oh, that's cool. Good job. All right,
Who did
now,
you have?
He had Kapoor.
Oh,
But see,
Radha,
he had calculus in high school,
okay.
so Dr. Kapoor, he went to his class, Calc 2.
It was easy though, I didn't mind it. It's just in high school for the AP exam, I got like a 3, so I was like, just repeat it over here. I'll get a better credit.
Good call.
Yeah.
That's smart. I got a 4.
But
You know, it's kind of mad I didn't get 5 as a high school senior.
I'm trying to go to college park, but they don't get 3, so only accept 4 and 5.
Yeah.
For the calc.
I got a 4, and I was going to Notre Dame, I was like, nah, I didn't get a 5. But anyways, I got to Notre Dame, I'm like, wait a minute, you know what I'm gonna do? I'm like, now I'm getting my transcript for college, this is my first time at college, I'm gonna take Calc 1 again. Because it's gonna be not only an easy A, I better get an A, number 2, I'm gonna be better at this stuff. And people go, well, you lose this semester, I don't care.
It doesn't matter. Yeah.
Smartest thing I ever did.
Right.
I had a stronger foundation, I saw the stuff I didn't make sense of before. I worked like 3 sections ahead of the professor every day. You know, I was relaxed. It was my first time at college. It was the smartest thing I ever did. So I'm like you. I like that.
So that means he's getting an
Yeah,
8? He's getting an
probably.
8?
Hey, what's true of you?
Just one.
And up at dx, right? All right. Now dv's the other part, which was what?
E to the power x.
All right. Now integrate that. You got to integrate it.
So that should
Let's
be
integral v dx.
e to the power x plus c.
Oh, and I'll put the dx with this, right? See, I'll put the ex ddx here.
Uh-huh.
The integral of v dx dx is just ddx.
We didn't put the c?
We will in the end. You can.
Okay,
You would. When we're done, we'll do that.
okay,
Very good.
okay.
All right, so here we go. Ultraviolet minus the integral of voodoo, right?
Uh-huh.
All right, U, V minus integral voodoo.
Okay.
U is,
Xex minus voodoo is ex and dx. Okay, so now
D, du. Good. Now, what's the final answer?
xex minus ex plus c.
You got it?
Okay.
Now, I want to let you know, if you had like, let's say like x sine of x, 5x cosine x, dx, dx, 3x e to the x. Notice there's no power difference. It's kind of obvious when you need integration by parts. Any of these. Trig functions, e to the x, you let u equal the x, you let u equal the 5x, you let u equal the 3x. Now, when do you not let u equal that? I'm going to go on this side. If you got a natural log, or if you have an inverse tangent. If you have either of these or an arc sine, like this is what you're going to let u equal to.
Oh, you don't let them to you too.
So all these, when you get this x sine of x, 5x cosine x, 3x e to x, what do you let u equal to? Let u be the what? The x,
X.
or the 5x, or the 3x, or any of these. But if you get any that has a what?
Natural log.
Natural log, or an inverse trig function like arctan,
Uh-huh.
or arcsine, because we haven't figured out those antiderivatives yet. But you do it by integration by parts. So can we do one? Can we do that one?
Yeah, sure.
All right, here we go. So when this is going to be ln of x, and let's see if we can do it. Remember, this is Calc 2. Now, natural log, that's what I want you to let u be.
Okay.
U is,
Natural log.
Yes.
then dv is just the dx.
Uh-huh.
All right, what's the derivative?
1 over x.
What's the integral of a 1?
X.
Good.
Good job.
Now, here we go. Ultraviolet minus integral v du. All right, roll it out. U.
Natural log x and x.
So I like to put the x in front. Is that what
Uh-huh.
that?
Yeah.
Look,
I use-
x, ln x, it looks better. Because
Uh-huh.
ln x gets sloppy.
Yeah.
X ln of x minus integral of
V du
X.
v.
and
And
du
what's
is
du?
1 over x.
X is crossed out.
And I should probably put a dx here, huh? And you're saying these what?
Cross out.
X is crossed out.
So I get an integral of 1. So let's see. What's x ln of x
Minus
minus
1.
the integral of a 1?
X minus X.
Yeah,
So-
minus x. So what's the answer?
X natural log x minus x plus c.
You got it. And you'll probably get sick of doing this every time. You probably just memorize it. You'll probably just go, integral of ln of x is x ln of x minus x plus c. Kind of like, do you have it memorized already? What's the integral of tangent of x from today? You might have it memorized. It had an ln in it.
I forward.
You probably eventually memorize it because you get tired of doing the use of every time. Do you remember it was secant of x or negative ln cosine of x? We're doing integration by parts. Do you like it?
Alright.
She's not
Any
taking
more? Any more? Do you mind doing
No,
any more?
no, I mean, that's cool. We can do others too.
Oh, I gotta show you something. Sometimes you gotta do like a repetitive thing.
Uh-huh.
So, today we saw this. Do you all recall that?
Mm-hmm.
U sub, oh, we won't do it now. What did we let u equal to?
X squared.
X squared, right?
Mhm.
All right. When we did x e to the x, I can't put that on your test, Cal, but we said integration by parts. Well, how about this guy? You go, what is that? It's an integration by parts, but you're gonna have to do how many rounds?
2.
2 rounds.
Huh.
I know, so you're gonna have to be careful.
You make u equal to x squared.
Yep, and then you do a whole thing, and you get the power to go down a little bit. You get this whole thing written out, and you get to this, and you go, oh, I got to do another what? Integration by parts.
Hmm.
Do you follow me? And it gets kind of annoying, actually. I'll be honest, I don't like to do this so much because I got to do integration by parts again. Isn't that cool though?
Yeah, it's interesting.
Interesting, yeah.
So
Very
yeah, it
interesting,
means you could really do this, but boy, it would probably take a while. It would.
It'd be kind of long.
That's a couple pages of work. Because you keep what?
50.
You keep trying to break it down, so you finally got the power to get down to the x e to the x, as you do 5 rounds of integration.
Remember I was telling you about Sylvanus?
Yeah.
He does all this proof on this book. In
Really?
the 1800 he wrote that book, and he did all the proof. He's like what you said, theoretical math. I mean, like he'll do all the proofs, like nothing like Larson or anything.
Hey, tomorrow,
Uh huh.
you know what we should do tomorrow?